Today I'm going to talk a bit about an unfinished revolution occurring in physics. Quantum physics has had a difficulty with merging with Einstein's theory of relativity. And I'm going to talk about this in the context of a recent lecture that occurred. Dr. Wilczek came and spoke. And we're going to introduce a memorial lectureship in his honor to continue what he started with his first inaugural lecture. So I'll start first by honoring Frank Wilczek. He honored us with a talk at UAB through the Integrated Systems Center. He earned a Nobel Prize for his work on developing the concept of asymptotic freedom, a property of gauge theory, which I will somewhat put into context later. I'm not going to try to give a detailed representation of the current standard model, but I'm going to give a very brief one just to make some points. Dr. Wilczek has focused a career on augmenting the standard model, the one we're about to talk about, by proposing new particles such as axions and anyons, as well as studying the concept of time crystals. As a scientist, his work has always been at the edges of the standard model, as many of the great thinkers, where many of the great thinkers have been, seeking the paradigm shifts that can bring us to better understanding of the natural world. There is a coming paradigm shift in physics. I think it's recognized across the board, but we don't really have a complete understanding. This has driven a number of different theories. String theories are in this category, but also other revisions of the standard model. It's only fitting that in Dr. Wilczek's honor, we will discuss the coming paradigm shift, the parameters of it, or at least what we believe the parameters are, and how it might relate to this standard model of physics. Quantum theory, embodied most directly by this standard model, underpins many of the most dramatic scientific and technical advances of the 20th century. And for over 90 years, experimenters have meticulously tested the theory without really calling its foundations into question. But there's a fundamental problem, however. The current standard model of physics is incompatible with general relativity. At the center of this incompatibility is a philosophical debate. There are a couple of different perspectives on how to look at the world. The anti-realistic perspective posits that the observer is the fundamental arbiter of all natural phenomena, and that all observers create the universe that they inhabit, and each observer inhabits their own universe. This allows for a number of different thoughts to develop a number of different theoretical outcomes, including multiple splitting universes and a whole variety of very fantastical concepts. Embedded in this is the idea that the future state of any given physical system is not predictable. This contrasts with the realist perspective held by Einstein and others that the universe actually does exist independent of our minds, and that this universe can be described by deterministic laws, and in principle, with enough information, the future state of a given physical system can, in fact, be predicted. So to talk about this in a bit more detail, and just to give some insight into where the model is starting and where we are starting, where our physics model is starting, as an exposition, I'm going to describe a fundamental model that informs quantum physics. And you will see, as I describe it, that the theory of quantum physics is positioned for a disruption. Current quantum physics posits, or actually demonstrates in terms of the experimental evidence, a dizzying array of particles and interactions. It considers particles, fermions, interacting via a series of force carriers, or bosons, and these and fermions come in a couple of different flavors, quarks and leptons. Bosons also come in flavors. We have gauge bosons, photons, gluons, W bosons, Z bosons, the Higgs boson at the middle. All right, so there's been a recent visual representation developed of the Standard Model that I think will be very illustrative and be very helpful on understanding the parameters of the Standard Model and understanding why it might seem like, at least from an outside perspective, that this is a model that can be positioned for disruption. So we have matter particles again. We talked about there being two varieties, quarks and leptons. Quarks come in two different varieties, up and down. Leptons come in two varieties, electrons and neutrinos. This is from Quigg's visual representation of quantum physics, and it was presented in Quanta magazine. So the point here is that, remember, this was developed from an anti-realistic perspective, meaning only observables can inform our model. So quarks, observably, have unexplainable rules. Solitary quarks are never seen. Quarks have partial charges. We don't know why. They come in various colors, quantum chromodynamics, red, green, and blue. They have a handedness. They can be left-handed or right-handed. The left-handed up and down quarks interact via weak and strong bosons, but right-handed ones do not interact via weak and strong forces, even though they seem to otherwise have identical or at least very similar properties, except that any group of quarks can be bound in a three-part grouping by gluons, the mediator of the strong force. Two up and one down quark creates a proton. Remember, these quarks are things we've never seen. Two down quarks and one up quark create a neutron. And there's a visual representation on the right. A proton and the neutron do not have color because they are a combination of the three colored quarks. And the charge of a proton is combined from the various charges of the quarks. So for example, if I have two up quarks, plus 4/3, and one down quark, minus 1/3, I get a proton. If I have two down quarks and one up quark, I get the neutron, which has no charge. These differences, again, these rules are not explained, and there's no attempt made to explain them. Leptons also have unexplained attributes. They differ from fermion. They don't have structure. They don't have color. For unexplainable reasons, a neutrino is close to massless. And again, for unexplainable reasons, we see left-handed neutrinos, but we never see a right-handed neutrino. It's never been experimentally seen. It's a theoretical object only. Another unexplainable portion, these quarks come in flavors in generations of three. Each generation is identical in all properties to the other generations except for one, mass. So a muon is a heavier version of an electron, and a tau particle is a heavier version of a muon, which is again heavier than an electron. Up, charm, and top quarks have similar properties, but one's heavier each one's heavier than the preceding one. In addition, just going to, this is called the CODATA, cooperative data assessment from fundamental physics. There are a whole variety of unexplainable constants. These constants inform this model, this standard model of physics, and basically allow this model to translate into the world we see. But these constants aren't explainable. They simply exist. They're observed. Okay? So this would be a version of the current theory of anything represented visually, or at least everything small. Because, again, as I told you, this does not fit with Einstein's theory of relativity. This only explains the world of the small. So we have fermions, quarks, leptons, photons, gluons, bosons, the Higgs particle, electromagnetism, weak and strong, and Higgs interactions, all on one form and you can see all the various lines connecting all these various objects together. And using this model, we can do a remarkable job of predicting the world that we see. And it's the basis of many of the scientific advances that have occurred. So the triumph of this model has been based on a very simple premise. The simple premise is that there is no underlying unseen or unseeable structure to the universe. The model rests rather on a single column, experimental observation. It is a remarkable triumph. And again, we're coming from the non-realist perspective. An unobserved theoretical underpinning is neither necessary nor is it desirable. It's considered from this camp that this underlying structure is not something that that perhaps we even have the capability of comprehending. Now Einstein, he recognized the power of this model, but for Einstein, quantum physics was a placeholder, a repository for observations in preparation for a paradigm shift. What is a paradigm shift? Normal science has been defined as the regular work of a scientist theorizing, observing, and experimenting within a settled paradigm or explanatory framework. This is a term that was come up by Thomas Kuhn. Structure of Scientific Revolutions is his book, and it was first written in the 1960s, but it's been updated. A paradigm shift, also defined by Kuhn, is a concept describing a fundamental change in the basic concept and experimentation practices of a scientific discipline. Lee Smolin, if we were to identify a modern-day gladiator for Einstein's realistic proposition that we can comprehend the fundamentals, if we were to identify that modern-day gladiator, Lee Smolin would be an excellent candidate. For example, to the left, he comments on the fundamental disagreement between Einstein, de Broglie, and Schrödinger, okay, three people in the realist camp, from essentially the remainder of the field developing quantum physics. Heisenberg, for example, and a whole list. I'll read it because I think it's worth listening to in its entirety. One quantum theory of the atom is great, but two are a problem, especially since they both reproduce the right spectrum of hydrogen. The two theories could not have differed more as reflecting the philosophies of their discoverers. Einstein, de Broglie, and Schrödinger were realists. Even if there were mysteries, they believed an electron was in fact a real object and somehow existed as both a particle and a wave inside a grander model. But Bohr and Heisenberg were enthusiastic anti-realists who believed we have no access to reality, we're not capable, only to tables of numbers which represent the interactions with the atom, but not the atom directly. Now I've added the bold here. This is from Lee Smolin's popular book, so it's very accessible, Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum, Penguin Press. Lee Smolin presents 5 principles to inform the model to come. First principle, background independence. The theory should depend on structure which evolves dynamically and does not require any outside matrix, meaning everything exists within the model. The model does not have to exist in any external space. Space and time are relational. This is the second principle. Specific objects occupy specific spaces at specific times, and space and time locations are always related for all objects. Third principle, causal completeness. All events have a discernible cause that is derived from within the system. No cause from outside the system is ever needed. Fourth principle, reciprocity. If an object A acts on B, then B must also act on A. The final, identity of indiscernibles. Now, if you want more detail on these, you'll have to read Smolin's book, because these are fairly meaty principles, but I'm trying to make them very brief. Any two objects that have precisely the same properties are in fact the same object. Okay? So how do Lee-Smolin's principles in quantum theory and the Standard Model connect? Now, I'm giving my interpretation. Others may have their own concept of this, but in terms of background independence, the Standard Model does not seem to satisfy this. Objects are assumed to travel through space and time, and the entire theory is imputed into a dimensionality. Objects have to exist within that. A photon exists in a space, in a time, and these clocks are external. Space and time are relational. Well, it does not really truly at the smallest level satisfy this either. Objects can exist in a superposition of state, occupying multiple space-time locations at any one time. Quantum tunneling being an example of how quantum physics explains how things can get to opposite sides of a barrier. It may satisfy reciprocity. It's unclear. It does satisfy identity of indiscernibles. Any one proton is indistinguishable from another proton in the model. But as you can see, current Standard Model does not satisfy Lee-Smolin's principles. So returning to the debate, the Standard Model of physics is based on the anti-realistic perspective. But a model based on the realistic perspective will satisfy Lee-Smolin's principles. Anti-realistic perspective, again, the observer is a fundamental arbiter. The observer creates the universe they inhabit. The observer's universe is different from the universe of any other observer. And there's a quantum uncertainty, a lack of predictability in the model. A realist perspective exists, is that the universe does in fact exist independent of our mind and can be described, is deterministic, and in principle with enough information the future state of any given physical system can be predicted. Looks like we have a little bit of an issue with this slide, but I think you can read everything. So in closing, so the purpose of that was basically to give a framework. Dr. Wilczek has been working in this space of this Standard Model, but on the edges, attempting to kind of push the model out to understand where it might break. And in honor of this effort, I would like to close by announcing a lecture series, the Frank Wilczek Lecture Series. Dedicated to the work of Dr. Wilczek, our lecture series will focus on addressing the coming paradigm shift in physics, including presenting our own proposed solutions. I want to make one other comment and another thank you. Dr. Weinberg gave us the great honor of attending our lecture. Dr. Weinberg is another Nobel laureate and extremely well known in physics, and we really do thank him for attending. And hope that he, Dr. Wilczek, and others can potentially come back and join us periodically as our lecture series progresses. Everybody, stay tuned, and we'll look forward to seeing you next time.